Hi, my name is Gene. I'm a new mentor from high school robotics team FRC 714 from Newark, New Jersey. These videos are for high school team coaches who want to help all students on their robotics team write code in a modern programming language, Python. With so many AI products around, your students will need to write code in Python a few years down the road when they graduate, even if they don't plan to become software engineers. If they're thinking of becoming any kind of engineers at all, Python will make them productive with most of the AI products and jobs. Today we're making a big step towards the kind of code that can win competitions, while staying very simple because it's written in Python. Let's do it. What does it take to win FRC World Finals for a student team from Philadelphia, like Team 321 did this year? We're looking at their code, and one thing you can spot immediately is you have this commands folder in which a bunch of little commands are put, and this subsystems folder, which contains the code for every subsystem of a robot in a separate file. Together, the subsystems and commands get connected inside of robotcontainer.java, like a lot of pieces of Lego in a big toy. This approach allowed Team 321 and many other winning teams to get where they are. This approach is called command-based robot, so let's do it. Today we have exactly one command in one commands folder and one subsystem in the subsystems folder. It's a start, and then all you do is you add more commands and more subsystems, and soon enough you get a robot that can win FRC World Finals. Together, commands and subsystems connect inside of Robot Container Plus, like this. Link in the description. Let's clone this code from GitHub. So let's open PyCharm. I'm clicking Get from VCS. I'm putting the link for this repository. The link is in the description of the video. It's called command rev tank. Clone. The code is downloaded, and as you can see, there is a subsystems folder and the commands folder with exactly one command and one subsystem inside. It's a start. First thing we need to do is we need to click the interpreter version and say add new interpreter and pick our version of Python, Python 3.9, to create a virtual environment. Hit OK. We will be using Python 3.9 and the virtual environment is created. Second, we need to go to requirements.txt to make sure all of the requirements, all of these dependencies are installed. For example, RobotPy. It is not installed, so I'm going to click Install the missing packages. You have to be connected to internet for this. Now, finally, after RobotPy is installed, here, and I'm just going to show you what's going on. We're going to use the Navex gyro on this robot, and we're going to use rev motors on this robot. So to download the appropriate dependencies to be able to code against Navex gyro and the rev motors, we need to run the sync command, which will download them from internet. Let's do it. The dependencies have been downloaded, and now we can code with Navex gyro and the rev motors, and let me show you why it matters. So this is why I'm green today. I have this green limelight camera staring at me, which is a part of the robot that was generously provided by a competitor team 8630, so I can make this video. which commands do we have here and which subsystems? For subsystems, we have a drivetrain. If I click on the drive subsystem, I see the drive subsystem class in here. If we look inside, it consists of 4 motors, motor left 1, motor left 2, which are sitting on left motor address K left motor 1 can, K left motor 2 can is the address for the second motor, and there is motor right 1 and motor right 2, which have the right motor 1 and left motor 1 addresses. What are the addresses? If you go to constants.py, you will see that each motor has its own can address. 1, 2, 3, 4, because they all share the same bus to which they are connected, so they are receiving the CAN messages. You're supposed to do it, you're supposed to configure them. I assume that you have configured yours. If you have configured yours with different addresses, for example 5, 6, 7, 8, you have to change them in here, and that will work. If we go back to drive subsystem, so it creates all these motors, and then it defines one method that we care about, arcade drive, which means you must give it the forward speed and the rotation speed. And if you give it some rotation speed and the forward speed, it will drive on an arc. That's why it's called an arcade. If you give it forward speed but 0 rotation speed, it will just drive forward or drive backward if the speed was negative. Finally, there is this one command which you can use to use this drivetrain system. The command is called arcade drive, and you give it the source of the forward speed, the source of the rotation speed. It's very easy to give them in form of lambdas, if you know what a lambda is. If you don't worry. Mostly, what this command does when it runs is it calls this execute function, which commands the drivetrain to go with the forward speed and the rotation speed provided to the command. How does the command connect with the subsystem? What you do in this specific case is in the constructor of robot container. It's very important to go to robot container class. You need to define a default command for the drivetrain. So you say my drivetrain self.robotDrive set default command, and you create an instance of this arcade drive command. What do we use for the forward speed? We use the left Y axis of the joystick. That's going to be the forward speed. What do we use for rotation speed of the arcade drive? We use the left X stick of the joystick. And of course, the arcade drive command needs to know which of the drivetrains to drive, in case there is more than one. This is it. That's all there is to it. In addition, just to make things a little bit more fun, you can define what different buttons do. This is done in configure buttons function, also in robot container. And you should encourage your students, and students should be encouraged to really put all the button bindings inside of a configure buttons function. So it's very easy to find them. For example, the left button is going to be a joystick button for our primary joystick driver controller, and it's going to reset when it is pressed, which is on true. It's going to reset the odometry, which is the X and Y of the robot on the field, to 0. In case you want to say, hey, right now my robot is at origin, reset. What this code does is it puts the X, Y, and the heading of the robot onto a smart dashboard. And it also shows you how easy it is to put anything you want on a smart dashboard. Also, if you press the right bumper, the robot will go slower, max output of 0.5. If you unpress the right bumper, the robot will go fast again. Let's try it. I'm going to connect to the robot's Wi-Fi network, because it's been given to us by team 8630. The network name is 8630. Connect, and all I have to do is I have to run deploy. And this code will be deployed on a robot. We're asked, what is the team number or robot host name? The team number is 8630. It is needed to know what's the IP address of the robot. Deployed successfully. First of all, we can fire up our driving station, FRC driver station. And connect to that robot to see how well that code is doing. Is it healthy or is it erroring on us? Here in the window you can see that it doesn't like the fact that there is no joystick. So let's connect the joystick. And green joystick connected, and I don't think it's complaining anymore. You can see my green joystick is here in the joystick section. If I move it, the axis of the joystick moves the left X and the left Y. So in theory, if I enable the robot and teleoperate it, I should be able to drive it. Before I forget, we discussed that there is this left button that resets the odometry or the coordinates of the robot. So yes, this drivetrain can know its coordinates X, Y, and the heading. Let's fire up Smart Dashboard and see how this is happening. Smart Dashboard, you probably have it if you have Driving Station or FRC Toolkit. Look, in the Smart Dashboard there is coordinate of the robot X, Y, and the heading, which way it's pointing, north, south, or maybe 40 degrees north. Now if I move the sticks of the joystick, robot will start moving, and the X is going up. Now I'm going to make it point 90 degrees to the left. The heading is changing, and the X also, because it was moving backwards. And now I'm going to drive it forward, but because it's pointing to the left, now the Y is changing. So these are the coordinates of the robot on the field, and you can use them for all sorts of cool things, at least for autonomous mode. Congratulations! Today we successfully switched from time-based robot to a command-based robot, and we're never going back. Next up is we're going to do the same with a swerve drive. Until then.